Okay, my first question to you is, at this point right here, where I'm scribbling green, okay, is there water left in your aquifer? Is there still some water in there? Okay? Can you calculate it? I gave you an equation earlier to calculate it, right? How much volume is left in your aquifer after a certain time. Now at this point here, let me make it a different color. Let's make it red. We just went through a period of recharge, right? Now you have a whole bunch more volume in there. So your recharge, without equations, just conceptually, is going to equal what? Those two dots are volumes, right? I talked about volumes. There's a volume left in your aquifer at the end of year 1, and there's a volume of water in your aquifer at the beginning of year 2. What's the recharge relative to those two quantities? So it's the volume at the start of year 2, right? And continue.
Yeah, so the Q naught subtract the 1500, you're subtracting what you emitted.
Okay, now remember these Q's are flow rates. That's just how much water is going through your stream, okay? The equations I gave you were for volumes, okay? That's what's in the aquifer, okay? So you're close. It's not really the Q naught, it's the volumes, okay? So this is the volume at the start of year 2 minus the volume at the end of year 1, okay? You still have a little water left at the end of year 1. And then at the start of year 2, you have a lot more volume. So the volume at the end of recession 1 we can figure out from the volume at any time after the start of the recession is the volume available at the beginning of the recession 10 over the time it took for the recession over the time it took to go to 1/10 of the flow. How much volume is at the beginning of year 2? We had a different equation for that. We had an equation that gave us the total volume available for an entire recession, right? That was the very first one I gave you, which was VTP equals Q naught T over 2.3. Now you have to use the right values for each recession. So at the start of year 2, in the upper right part of this diagram, I showed that they're actually different recessions. So recession for year 2 is 1,500 cubic meters per second. Time to drop to 1/10 of that is 7 months. For recession 2, or for recession 1, excuse me, it was a little lower, 1,100 cubic meters per second. Time to drop to TI is 7 months, but that recession goes on for 9 months, and this is kind of a key part of the equation right here. This is going to be a long recession. It's going to go on beyond what they normally do. There's going to be a lot less water in there. So go ahead and calculate and see what you come up with. Okay. I know up to this point this has been kind of muddled and a little confusing. I think I can clean it all up for you now that you've had a little chance to play around with these two equations, okay? So if you're at all muddled, now's the time you really want to pay attention. I'm going to try to make this as simple as possible, okay? We have two equations here. Both of them provide us with a volume of water that's in our aquifer, okay? When I say base flow available at the beginning of a recession, that is how much volume of water is in the aquifer that can eventually migrate into the stream and be carried away, okay? So this first equation on the left, VTP, that is the base flow available at the beginning of the recession, the volume in the aquifer at the beginning. So that equation only pertains to 2 points on our graph. The beginning of a recession. So that equation can only be used to tell you the volume of the aquifer at 2 places on this graph. The start of year 1 or the start of year 2. Okay? That's the only 2 places that that equation gives us any information about. Okay? So it tells us how much volume of water is in our aquifer at the beginning of those recessions. And then over the next many months, that water is going to move into the stream and get carried away. This second equation, VT, tells us the base flow, the volume of water in our aquifer anytime after the start. So it's good for this entire part of the graph here for year 1, and this entire part of the graph here for year 2. All right? We said a minute ago the recharge is the amount at the end right here, subtracted from the amount at the beginning, right up top here. Can you calculate the amount at the beginning of year 2? Yep, by using the first equation. Can you calculate the amount at the end of year 1? Yep, by using the second equation. Okay? Any questions on the concept and what equations to use? I hope that cleared up your question of which was which. Did it? Okay. Yeah, Keaton.
So for the VTP, you use the QO of the second equation. So that's all centered around the second. And then for the VT, you use that for the first year.
Okay, yeah, the way I wrote this out is kind of backwards from the way the graph is, right? So this equation right here, the VTP, tells us the volume of water in our aquifer at the beginning of recessions. We have 2 beginnings of recessions on this plot, right? We have the beginning of year 1, we have the beginning of year 2. For the question I gave you, I want to know how much recharge between the end of 1 and the beginning of 2. So you would use this first equation for the beginning of the recession year 2. Okay? I gave you some data up in the upper right. Recession 2, Q0 is 1500, right? T1 is 7 months. T1 is the amount of time it would take to drop to 1/10 of Q0. So the amount of time it takes to drop from 1500 down to 150. That would be 7 months. So that first equation, you plug in 1500 cubic meters per second for Q0. You type in 7 months, convert it to seconds for T1, and that should give you the volume of water in your aquifer at the beginning of year 2. And from that, you're going to subtract whatever was left in your aquifer. You had some water left in your aquifer. It didn't completely drain out, right? If it went completely to zero, which it never does, but if it did, your recharge would just be, in this case, your VTP for year 2. Does that make sense? But because there was still some water left in there, we have to subtract that, okay? And that's where the second equation comes in. This tells you how much is left at any time after the start. We want to know how much is left right there after, and I put this up in the upper right, 9 months. Okay, that was kind of a longer one. So it lasted a little longer than normal. And I think that was the question that you had at the beginning, is the first equation that I have listed only tells you the total amount that's in there. Okay? Sometimes the recessions last longer, sometimes they less long. So just to sort of put numbers to this then. So recharge equals volume at the start of year 2 minus the volume at the end of year 1. Volume at the start of year 2 VTP Q naught T1 over 2.3 that equals 1,500 cubic meters per second times 7 months. Over 2.3, but we have to convert 7 months to seconds so that our seconds cancel out. 1 month, 30 days, 1 day, 24 hours, and then 1 hour. I'm running out of room, so I'm just going to make it 3,600 seconds. 60 times 60. So months cancel. Great. My tablet is not happy with me. So months cancel, days cancel, hours cancel. We're left with seconds. And when I multiply this out, let's see what I get for answer. I actually got 1.18, but I'm just going to round it to 1.2 times 10 to the 10th meters cubed. Okay. That's the volume at the start of year 2. Volume at the end of year 1. We can use our other equation. VT equals VTP 10 to the T over T1. We've actually calculated VTP several times now. 8.7 times 10 to the 9th meters cubed over 10. T was 9 months. T1, time it take to drop to 1/10 of the original flow, was 7 months. Those cancel. You don't have to change those to days unless you want. If you multiply all this out, I got 4.5 times 10 to the 8th meters cubed. And if you subtract one from the other, I ended up with 1.15-ish. You might be off by a decimal point here or there because I rounded and maybe you didn't. Times 10 to the 10th meters cubed. So you can check this as you go through this at home. If you have any problems with this, let me know. But that's the general way of doing it. If it seems a little confusing, work through it a couple times. I may or may not have this on the exam. I haven't decided yet. Depends how many questions I get through the week, your level of understanding. I want you to understand it before I test you on it. So if there's lots of questions about it, I'll assume people need help and maybe I won't ask it. But if you guys seem comfortable with it, maybe I will, maybe I won't. Yes, sir?
So I'm a little confused about VTP.
VTP?
Yeah.
Yeah.
So when you use it in the first equation, you got 1.18 times 10 to the 10th meters cubed.
1.18 times 10 to the 10th meter. Yes.
But why?
In this case, I got a different one?
Right, in your second equation.
Second one, I got a... Why did I get a different one?
Because you have to use your year one.
I have to use my year 1 Q naught, which is almost a third less. So it'll be smaller. Yeah, so you should use 1100 for Q naught for that first year. It started out with less water in it. Think of it that way. So yeah, so that was for year 1, and this value was for year 2. Slightly different amounts. All right, our next section goes into groundwater movement. So we're done with surface water now. Surface water, groundwater interactions, we're done with this. Now we're going to talk about just water moving through groundwater systems, and particularly with wells. We're going to be talking about wells the rest of the semester. Drilling wells is where we get data for groundwater systems. It tells us an awful lot about how water is going to move, why water moves, what it's going to do. I'm just going to get started today. This next stuff is not going to be on the exam, okay? There's not enough time to do it thoroughly, but I want to introduce it to you, and then we're going to come back to it in 2 weeks, okay? We'll come back to all of this, but let's just spend about 5 minutes, maybe 10, sort of setting it up. So this is about movement of water in the saturated zone. And in this example, I'm going to give you a confined aquifer. Remember, a confined aquifer is one that has a confining layer. So water beneath the confining layer may be under pressure. So let's sort of draw a surface here. And let's put in a couple of wells. One well there, one well here. Let's make a confining layer right here. So here's a kind of a shale or clay layer. And it's putting water under pressure. And this case, your water level rises in your well up above the confining layer. So this is what we would call an artesian system. And in this case, we're going to have the water rise up a little higher. So again, this is our confining layer, Cl. This is our aquifer down here. Which of these two wells taps into the aquifer that, let me rephrase that. Which of these two wells has water with the most energy? The taller one, right? Okay? So you can think of this as having more energy. If that has more energy, what's going to happen in this system is, in general, your water movement is going to go from higher energy to lower energy. So just by looking at the level of water in these wells, the water movement in your aquifer is probably going to be from right to left in this diagram. And to illustrate that a little more clearly, there's a couple types of energy possessed by groundwater. It's actually a lot of types, but there's only 3 types that are going to matter for determining how water is going to move in the ground. Can you guys think of any energy that water might have? We talked about energy a little bit earlier. That moving groundwater might have. If something's moving, what kind of energy does it have? It has kinetic energy. Your kinetic energy, EK, you may remember this, is 1/2 mass times velocity squared. Mass is in kilograms. Velocity is in meters per second. Not squared, just meters per second. And your unit is kilogram meters per second. If you square that, it's meters squared, seconds squared. Can you think of any other types of energy that groundwater might possess?
Potential?
It does have potential. Potential energy, you might remember this from discussion we have earlier, is mass times gravity times the height. I'm going to use Z above a baseline. me put this on the next page. And we said potential. Mass times gravity times height. So mass is in kilograms. Gravity is in, hang on, meters per second squared. Z is the height above a baseline. We measure that in meters. Let me just elaborate on this for a second. For our purposes, we say height above a baseline. Whenever I talk about potential energy in class, I usually talk about a rock above the floor, okay? And you drop it, that potential energy is converted into kinetic energy. The baseline that we use in groundwater is typically sea level. So it's basically elevation. What kind of units do we have? Kilogram times meter per second square times meter gives us the same unit that we had above. The third type of energy that forces groundwater to move is pressure. Pressure equals force per unit area force equals mass times acceleration. Mass is in kilograms, acceleration is meters per second squared. That unit is a Newton, so our unit of pressure is kilograms per meter second squared over our area, which is in square meters. And you end up with kilogram meter second squared, which is also a Pascal. If you've had me, we've gone through this before. So the total energy is going to be all three of these added up. Total energy for some sort of volume of water is going to equal our kinetic energy one half. What I'm doing now is I'm actually switching out density for mass. Density is just mass per unit volume. So if we have the same volume, that water we're talking about in each of these cases, we can use density, okay? Will give us the same value. So that's our kinetic energy term. plus our potential energy term. Again, rather than mass, we'll use density. It's going to make the numbers come out nice here in a minute. Times gravity, times height above a baseline. And I'm just going to use P for pressure. I'll rewrite this on the next page. Okay, so this is our kinetic energy term. This is our potential energy term. And this is our pressure. This is a little trick that a scientist named Bernoulli came up with. If you divide through by density, you get, instead of energy per unit volume, you end up with energy per unit mass. If we divide that first term through by density, what do we end up with? Density cancels out, right? So we're left with v squared over 2. Plus our next term. If you get rid of the, if you divide through by density, density cancels out, you get gz. And your pressure term is going to be just pressure over density. What about groundwater movement? Is it typically fast or slow?
Slow, but it depends on what you're going through.
Depends on what you're going through. But as it turns out, in almost every case that we will cover, this velocity term is going to be really, really tiny. What does that make this entire term? Really, really tiny. In fact, it's so tiny that from this point forward, we're going to ignore the kinetic energy term. It's only when water moves through something like loose sand, where it moves really fast, does it become important. Okay? So that's kind of cool. We just got rid of one of the terms. Now what we want to do is divide through by gravity. When you divide your energy total per unit mass by gravity, you get something that hydrologists call hydraulic head. It's simply a measure of energy. Get used to that term. You can use it the rest of the semester. Okay, if we ignore kinetic energy because the velocities are so small, if we divide our potential energy term by gravity, what do we get? Just Z. And what is Z? Just the elevation, okay? Plus P over density times gravity. This term right here, it's kind of messy right now, right? It's actually not. It's actually super simple unit. Pressure, let's go back. Pressure was force per unit area, right? Force is kilogram meter per second squared divided by area, meter squared. Okay, so that's our P term. Density, what's our units for density?
Mass per volume.
Kilogram per meter cubed. What's gravity? Meters per second squared. Okay? Can we do some canceling out? Kilogram goes away, right? Meter per second squared goes away, right? What are we left with right now? If all this cancels out, we're left with 1, right? If all this cancels out here, we're left with 1. We're left with 1 over meters squared over 1 over meters cubed. You guys know what unit that is? You'd have to multiply all this by the inverse. This becomes 1. Over down here, you have 1 over meter. What that means is that this entire thing right here, if you reduce the terms, it becomes meters. What did we say Z was? Meters. So this hydraulic head is simply how high up above sea level the water is. What's really cool about that, and it might not be apparent, I'm just going to leave this, we'll do this again in a couple of weeks, is that the energy of groundwater can be measured as a height above sea level. Let me just write this out on the next page again. So we have H equals Z plus P over density gravity. Again, this is called our hydraulic head. Its units is meters. This is called our potential energy term, but it ends up being simply an elevation. So we call this the elevation head, also in meters, plus our final term, which is called our pressure head, which is also measured in meters. So if you go back to that little diagram I had earlier, let's see, where we had two wells, we had a confining layer, and then we had water levels rising to different heights in our well. This level right here is our total head, our total height above sea level for our first well. Here's our total head for our second well. Write that a little better. Which one has more energy? The second one, right? And total head is a combination of the elevation head plus the pressure head. Where's the pressure head in this diagram?
It's the energy that's forcing the well up.
Yeah, so it is actually that amount of height. That is going to be our pressure head, okay, for well 2. And this is going to be our pressure head for well 1. What's our elevation head?
The distance from the groundwater to the surface.
It's from sea level, remember. It's potential. So it's actually from the base of the well down to sea level. I'll give you an example. The second one right here, okay, HT2. Let's say that elevation of the top of the water right there was 5,260 feet above sea level, okay? And the base of the well was at 5,200 feet. How high is the pressure head in feet? What's the total head in feet? $5,260. That's the height. Okay? The height of the water has two components. It has pressure and it has elevation. Elevation is from sea level to the base of the well. So what's the elevation head? Should be 5,200 feet. So what's the pressure? $60 feet. So in this case, 5,260 equals the elevation head of 5,200 plus pressure head of 60, all in feet. Could be meters, could be feet, whatever we want to use as a unit. What about for this example? Let's say the base of the well is at 5180 and total head is 5230. What's total head? 5230. What's the elevation head? To the base of the well? 5180. How much of that energy is due to pressure? Difference between the two would be 50 feet. Like I said, I'm not going to cover this on the test. We're going to come back to it. But this is the stuff we're going to use the rest of the semester. Pretty much every class from this point forward, this is what we're going to be using. Okay? I'm going to go through all this again in 2 weeks, just so that you're all comfortable with it. I just want to throw it out there, let you look at it. Don't worry about it for the exam. Cover it again. Do you guys have any questions? Okay, if you do have questions this week, let me know. I'll help you through email. I'm even willing to do a little PowerPoint and put it online if you need more explanation on things. Let me know what you need from me.